So let's say this find, I don't know how abbreviated you want to be. It's care poly, okay, or
Yeah.
characteristic polynomial of matrix. Okay, and no determinants appear. Yay. And iterative. Different people have different comments about the numerical, so-called stability. Like if you do it for a huge matrix, perhaps the errors will. But for any, reasonable size matrix, it would be much faster. Probably it's built into some computer algebra. My guess is some of them use it internally. Okay. So Monsieur Leverrier, in the English, they tend to coalesce his name as one word, Leverrier. Was an astronomer in France, and here's a brief bio. And Faddeev picked up on this later, so probably when much more was known about linear algebra, and he realized you could kind of slick it up. But the notion, I think everybody sees this as a like a one-line comment when you're doing they'll say, oh, you can use traces to find there's a relation between the traces and the characteristic polynomial. And then they write 2 lines and they never tell you why, what they're doing, and can it be generalized. So this is the answer to that question, if that's ever interests you. So the technique here is to find coefficients using traces.
So Philip, is this expected to generalize to infinite dimensional?
That was actually a good question, because you would have the feeling that if some method would, this would be it. So I didn't see anybody do it, I mean, the famous question, you could say something like, oh, for a compact operator with a discrete spectrum, something like that, maybe it would work. I don't know. So, okay. So I managed to compress various pages. It managed to compress various pages of papers. Whoops, what's the matter here? Okay, sorry. I managed to compress many article pages ranging from 10 to more into 2 pages. And so this is what's called, so the subtitle is Advanced Mathematics from an Elementary Standpoint. Usually everybody wants to show how smart they are and that they can redo elementary stuff in a sophisticated way. So I decided that we're going to do this fancy stuff and show it's just algebra 1, long division, which you may or may not like. Okay, and then we should have an example. You want an example? I'm not sure if I even have an example for the ultimate result here. I think my favorite polynomial is, if I'm going to use f of x, is going to be a polynomial. That's 3. Probably everybody here can do this fast. Can say something like it. I think you get all negative. So one thing you want to substitute 1 in here. So write your x squared minus 3. I think everybody, so you write down your x, you get x squared minus x. And then you subtract, so you end up with minus x minus 3, and you get what? Minus 1 again, plus 1, minus 2. So I think you can see x minus 1 squared, right? Do you see this here? From x minus 1 squared. So you can sort of guess the answer. I think it's supposed to be I get minus, is that right? You get -2, right? If you put in 1, you get -2.
Yeah, you get the plus one.
So note, so the last term here is f of the number. So I'm going to call this guy t. And this guy is going to be f of t. So that's the last guy.
Okay, you have, sorry, because, every country has a different way, right?
Yes.
So you have a polynomial. Now, on the left side, this is by what you divide,
Dividing the
and
divided
at the top is the result,
quotient, yeah.
and it shouldn't be x minus 3.
Plus or minus.
No,
That's your question.
Oh, I see.
no, you just
So-
bring it down.
Yeah.
Is that right? Okay, yeah, okay.
Close enough.
Are you sure we did that right?
You're not doing long division, you're doing something related.
Yeah, we're doing long division.
Yeah.
You know,
It's just long
then it would be
division.
x. Oh, x minus 1, not x plus
He
1.
didn't, yeah.
Yeah, so this is mine, I think
Minus
this is
eight.
-4. Yeah, I think this is.
I think the
-4.
confusion is why did you pick x minus 1 and not x plus 1?
No, I just picked this
Yeah, we
number,
just
I'm just
randomly picked
substituting
it.
1 in.
Oh,
So
yeah, you
what
get
it-
-1.
if you want to
Yeah,
substitute
so-
t, you get 4, right?
Yeah.
If you substitute t in, then you do x minus t, and the remainder is the result of the substitution, that's the remainder. I'll write it out again, like a couple times. Now, if you remember your math something, you have so-called synthetic division, where you don't have to write all that unless it's out. So you do it by this way, you write the coefficients, 1 minus 2 minus 3, and you write here the number you're substituting. You want to see if it's a root or not. And so here's the this is actually the recursion use. You multiply by this guy, and then you add, multiply again, and you add. Now we see the correct image is -4. Now here's the bonus. These are actually the coefficients of the quotient. Okay. So here's what I'm going to do is we're going to call this something like this. We're going to call this guy y0, y1, y2.
Philip, could you go slow on that?
Yeah, so let me put a t here so you can see what happens. You bring down the 1, this becomes t. You multiply by t. Okay, and this guy's t minus 2. This guy's t squared minus 2t. And this guy's t squared minus 2t minus 3. Notice that's my function. That's my f of t. This is f of t. So these guys I'm going to call like y0, y1, y2, so on. If you're nth degree, we're going to have n y's quotient. These are the coefficients of the quotient. And the recurrence, you see, if you do, so we're going to start with 1, this will be c minus c2. So y0 is 1, but then we're going to go ty0. So this is ty0 plus c1. The idea is in a minute, you can see it's real obvious what the recurrence is, right, in a minute. ty1 here. So y2 is going to be ty1 plus c2. Okay? Now I didn't prove, in a second we'll write it out and prove it, but you can see what the recurrence is at yk. This tyk minus 1 plus ck. So that's the guy. So that gives you so that's why this method, now the point is they never prove it. They just say, oh, you can do this. Okay, so I think it's worth writing out the proof because you'll see what the things are. Okay, so that's this and this. These guys do this. Is that all? Do you remember doing this in like, I don't know, 7th grade or 8th grade or?
So why did
grade?
why did you factor it in the first place? Why do you need a factorization?
Just so I can get a nice polynomial that in case, if you want the roots, for example, if you did now put in x plus 1 here, right?
Yeah.
Or you put, not plus 1, but put -1 here, right? I'm sorry. You put
Yeah,
x
right.
plus 1 here, then you'll get x minus 3.
And then
Yeah.
0 at the end.
Actually, what you do is you don't want a root. I wanted to make sure I didn't have a root.
Yeah,
Right, because by not having a root, then you can see it's the actual function.
Right.
If you have a root, you just get 0 every time you
Yeah,
realize that Oh, I know, I'm actually recalculating. So you can sort of get the idea. So this is what I guess Leverrier noticed, right? If you know these y's, which you can get, of course, it looks like you need the c's. Well, you need the what we'll see is you actually if you knew these y's, you could solve for ck, right? If you knew them. But the thing is, so it's recursive. If you know the c's up to a certain point, then you can get the y's, and then you can get the next c without knowing it. That's that here. Okay. All right. So let's see if we can. So this is the key calculation thing. I think it's better instead of trying to do the long division. I did in the handout. Right, in the handout, I did the long division. If you want to see that, fine, but we're going to do it here by hand. So I'm just going to do a simple case. So I'm going to write, so this is the key thing. So we're going to write, so f is a polynomial of degree n. And it looks like x to the n plus c1 x to the n minus 1 plus plus cn. Okay, so the subscript on the c tells you how far down the line you are. I think it's a very handy handy way of counting. Okay, we're going to write this as x minus p, and then we're going to see something pretty amazing here. This is the quotient. Well, now I would write the remainder here, but since this is linear, the remainder is just a function evaluated at t, right? Let's do that real quick. Write an r here. Let x equal t. This drops out. F of t. Okay. So that's sort of the proof of the end of this. Okay, so that's the basic equation. And we're going to do a calculation here. Let's do this way. So the quotients are y1 and y2 as you go down. Okay, so it's analogous to this
Yeah, each doing n equal 2, so yeah.
as you go down. So this is actually n is equal to 3, right? Because the degree of f is 3.
Oh, you multiplying that, not divide, okay,
Yeah.
okay.
Thank you. Yes, good point. It's good that you said something. Okay, yeah. Okay, so let's do this sort of a smart way. So do x first, x cubed, I'm going to write the x power first. And then we do minus t. You see when you get squared t minus t by 1.
And with an x on that, dy1.
Huh? There's the x. Thank you. That's the whole point, right? It's to match them. Okay, so now it's easy. Now we're matching the coefficients, right? We don't have to. Okay, just get this. So this would be x cubed. This would be C1, C2, and C3, right? I did something that's missing here. So I set y0 equal to 1. Okay, now this should be C1 should be y1 minus p. So I'm going to write that as t by 0. Okay, C2 is what? Y2 minus ty1, that's right. Except C3.
What happened to y1 x squared?
Yeah, I'm missing something.
Y1 x squared.
In the
Yeah.
first row.
X times y1 x is.
Yeah, it's in the top row right there, that x squared y1.
Oh, it is there. Oh, yeah, okay. And
Yeah, I
then
forgot
second-
y3. I forgot the x cubed, the other term. X squared, this should be.
Hmm.
X and
Yeah.
y2.
Did you enter? Right, right.
See, I have a y3 here. There's no y3. I think I was doing a fourth order one, and I reduced to 3.
Yeah, in the handout, we have a fourth order.
Yeah. So you should be getting, so y1 is py0 plus c1, right? y2 is py1 plus c2, and then you get that recursion. So what about c3? Should be y3. I don't see a y3 anywhere. Where did I? Let's see.
Well, your multiplication, there is, oh no, you have there. Well, the last term is just 0 minus t,
Yeah.
minus ty. So C3 is minus ty2.
Yeah, actually, okay. Okay, so that might be what we want, right? Okay. It should be. It should be fairly easy, straightforward. Y x squared t x t. Because somehow I have a y3.
Because the
Oh, just go ahead and put y3 here.
Yes.
Yeah, see, this is because this is the cubic. Yeah, you need a constant term. I'm sorry. Yeah, so the constant term is y3. Yeah, that's fine. So this is y3 minus y3.
Why is the constant term not minus ty2?
Yeah, so now when you subtract, you get y3. This is your polynomial, right?
In general, yeah.
This is your polynomial. This is your quotient multiplied by x. So now you have a y3 in there.
But that's not
Y3.
equal to that then, right?
Huh?
It's not equal.
y3 has to be 0.
There's no y3 in the first in the product you have, right?
Yeah.
If you want a y3, you need to start there. Do you have a plus y3 at the end of that? Like that's the remainder? Like you have the x minus t times the quadratic plus
Oh, yeah,
Y3.
Yeah. Thank you. That's the point. This is yn. I forgot to say.
okay.
There we go.
Thank you very much. So you have to add that back. You add in the remainder. Thank you.
Okay.
Yeah. Actually, it's real important to recognize yn as the remainder. So when you have a root, when you plug in something that's a root, yn will be 0, which is what, but we know it's not, this is generic, so we don't know it's 0 yet. Thank you. Yeah, it's the plus the remainder. I knew there was a reason why you had to add that in. Okay. So everything is kosher. y3 is py2 plus c. Okay, q. So notice that the indices here match, and this guy is always the previous guy. Okay? All right. Okay. So let's do a little bit of things about polynomials. Now, let me write one more thing here real quick, because this is really kind of cool. So f of x is x minus t, uxt plus f of t. See, this is sort of the basic thing. And of course, you're always talking about algebra checking. Notice that there's no t on this side. The t's totally absorbed. It's kind of, at first you say, wait a second, it's impossible. You can write this in a really beautiful way, which should, remember Newton is I should have mentioned that Newton is the guy really behind this calculations, this element E. And you can see where calculus is coming from, exactly this. So this QXP, which looks so strange, is actually your famous beginning of calculus, first aid. Okay. Here's another thing I just noticed today, kind of obvious. If you switch x and t, so this is equal to q of t and x. So x and t play completely symmetric roles, even though it looks like it doesn't here. So it's really, so whatever this expression is, which I think we might have to write out in full generality, is and it won't be obviously symmetric. Okay. So if you want to just introduce a little notation, so f of x you can write ck x to the n minus k, x to the n plus k equals n to n. So there's n coefficients. It's degree n and there's n coefficients. So I want to say a little bit more about a polynomial. So if you have a polynomial and you write it this way, you can differentiate it, right? So this is like after a little bit of this stuff. So this formula will be crucial later on. So just keep track of that. And here's something you may not have seen. So you can write f of x as a product of x minus x1. Well, these are the roots. Right? Now when I have a product, one of the tricks you learn in calculus is you take the logarithm of the product. So log f is simply log of x minus x1 plus blah, blah, blah. And now I can differentiate this. And if you remember the derivative of log f.
You mean natural log here.
Yeah, I learned the old fashioned notations. Like f prime over f is equal to what? Well, when I differentiate this guy, it's just 1 over it. It's a really beautiful thing. 1 over x minus x1 plus. So f prime is simply f times sigma 1 over x minus x. Kind of a cool formula. Now, what we're going to do is the fact that these two formulas agree is a key step in the thing. All right. And that's it. You don't have to know advanced math or anything, you know, like everybody makes these fancy comments, and I'm just saying, what the heck not you're doing it. So I think it's really beautiful. Okay, so let's see how to do that. Let me see if I don't know how general you want to write this thing here. So you might want note. Let's see what the y's look like. So y0 is 1. Y1 is ty0 plus c1, which is t plus c1. Y2 is t squared, so multiply by p. And I think in one more step, you see the pattern of this guy. Isn't that cool? So what it is, it's the pieces of the polynomial. You see, so if yn, you see now what yn is the polynomial, the full thing. So yn is it just got the t, and as you luckily remind us, that was the remainder, right? Yes, so that's where the yn came from. Yeah. Okay. So you have to unfortunately write this out. So y, say k, is sigma t to the k. I think I want to see, let's say t to the k plus t to the minus j, cj. Here goes from 1 to k. So you see the choice of indices is really easy this way. So as you go down again, the C tells you how far you've gone down the line. Okay. Okay, now we're ready for the next big step here. So we're going to let, I did already, but let's.
You want TK plus that sum?
Huh? Yes. Good grief. Thank you.
Yeah.
Right, yeah, thank you. Just polynomial.
Yeah.
Okay, so let xn be the roots of f of x. And again, you can either do this completely algebraically and then you can substitute numbers in later. So you don't have to worry about multiple roots or weird stuff, anything like that. Okay, so let's go back to our favorite expression. P, ux, P. And we're going to let P equal xi. And of course, the miracle happens. This guy's history now. So you get, you'll see, I'll leave this up maybe because you're going to get f of x is equal to x minus xi. Q of x xi. Okay, now here's the point. Let's solve for qxxi. So I don't know if you've done these kind of exercises, but if you have where's my polynomial? I'm at x, what do I have, x plus 1 times x minus 3. So the idea is you're just blocking out a term as you go. Now, what's cool is this theorem says if you do that and you add stuff up, you can get the derivative back. So it's a really amazing. There's all these sort of elementary identities that you get here. So this qxxi here, of course, so if you have only two, pretty easy, but if it works in general with this method. So f over x minus xi means you're blocking out a term, right, in the product. Okay. So qxxi, blah, blah. Okay. Now what is qxxi? It's the sum of yk evaluated with p replaced by xi times x to the n minus k minus 1. I don't know if I had written this down or not. I'm going to suppress the summation. Let's see if we did that when we had the quotient. Let's just go back a little bit to what the quotient looked like. So the quotient, for example, when n was 3, you got x squared plus, no, the quotient. So let's say y2 looks like what? It looks like p squared plus c1p plus c2. That's the y, and the quotient was like the quotient was like x squared plus 5x plus y2. So n is 3, so you're going to start with 1 degree lower, and then you're just going to bring in the y's. So you're 1 degree lower, and you're bringing in the y. So the kth guy down the row is yk. But starting with n minus 1, not n. Is that okay? Okay. I know we shouldn't skip any steps. Is it Steve totally?
You have a lot of time still.
Okay. I should have probably written this down
Is it in your notes
to
here?
begin with. Did I write that in the? I think at the very bottom, it shows you what the y. So I was using different coefficients, but yeah, here it's at the top. Equation number 2 is your quotient. Okay, so it starts actually. So it looks like you're starting at 0 here, and you're going n minus 1. Okay. All right. Okay, so it's important because we want to actually write all this stuff out. Okay. So we need like a huge thing here. It's not too bad. So this is going to be a double sum of so what does y look? Y look, remember it starts with the kth power. So it's xi to the k, and then it goes down. It's ck. Okay, so that's yk. All right. And then we're going to shove in an x to the n minus 3 minus 1. Okay.
What are the double sums?
The double sum is over.
And
There's no, actually,
I already summed, yeah.
I wrote the sum out. I wrote this out.
Yeah.
It's a double sum, but we wrote one. I wanted to be more explicit, so thank you. Okay. So here's the trick. So let's see, quotients, the quotient, polynomial. So we did this, this, and this. So the power, what do the power sums mean? So if you have a bunch of numbers, so the digression, but that important one. Power sums. So underlying all this is the theory of symmetric functions, which we don't get into too explicitly. But if you have a bunch of numbers or variables, let's say x2, x3, you define a symmetric function by picking an exponent, let's say 5. So that's a real easy way to get a symmetric function. Everybody's familiar more with the trace, right? You take x, say, or the sum. Everybody says, okay, that's your elementary function. But you can do it this way. You can make any power you like. So those are called power sums. I use P5. Some people call it S5, P5. You can argue about it. Okay. Now look what I've got here, folks. I've got xi to the k. If I sum that out, I will have eliminated a variable, right? I will have generated the power sum. And this is sort of the missing ingredient here. Let me see if I can write this out. Okay, now let's look at this for a minute. Look at this guy here. This is this here, and this is this, right? Now, what did we just say? If we sum these up, we get f prime. Not bad, huh? So f prime, which is equal to ck n minus k x to the n, you know, that everybody knows that formula from calculus, is equal to the sum of the q's. Which is equal to sum, this is a double sum now, yk of xi, x to the n minus k equals to 1. Right? Now, if you want to, you can write you can write it also this way with the power sums, pk, c1 pk minus 1. Okay, now look at the last term here. This term is cold. So when you add it up n times, what do you get? nck. Okay? You get nck. And then you get your x to the n minus k minus 1. Okay, guess what? This guy must be equal to that guy. And it must be equal to this sum right here. Okay, so that's the key thing. Now we almost there. Remember the YKs are generated recursively. So if we get the YK and we can get the next CK, then you're home free. So that's the idea.
But you don't mean a double sum there. No, do you? Over I and K both?
Yeah, K and K. And again, you don't need the double sum, do you?
Do you or
No, the
don't?
first
No,
sum
I
is
do.
over I.
I'm
do,
summing
yeah.
over I now.
Yes.
Yeah, now I need it. Thank you. Very good. Okay, cool. Okay, so what is it now? So so there's two ways, denouements here. This formula here what are called Newton's identities. And I looked it up. I've looked at like 10, you know how when you start looking, you go crazy. Wikipedia, Schmikipedia, everybody, they all have different proofs. I've never seen anybody, this proof I'm guessing is Newton's proof because it's the kind of thing you get by fiddling. You know, and you can see he's looking at f of x minus f of t. I mean, you know, like calculus is brewing in his mind. So these are actually Newton's identities. I bet you've never seen a proof like this before, right, John? I don't think it's, huh? I mean, if you look this up, everybody says, here's my way of proving Newton's identities, and you can use symmetric functions, you can use power series, you can use calculus, you can do everything. That's it, you're done. So what are Newton's identities? What they do is they express CK in terms of the power sums. And this is the formula they never told you in your linear algebra class. The next line after saying you can express the C in terms of the traces, this is the formula that you could tell me. By the way, do you see what happens here? This is a crucial observation. Look at this guy. Goodbye. He's gone. And that's essential. Why is that important? Because it proves that the formula is independent of the dimension. You know, if you have an n sitting in there, you'd be saying, help. I didn't discover anything useful. Okay, so these are the famous Newton identities. Okay, now what is the Leverrier-Faddeev thing is to go this route. All right, so let me write that down. Hopefully this is the second page. It should be almost. Okay, so CK and K is equal to the sum of YK on this side. Now, what does YK of Xi mean? This is Xi YK minus 1 plus CK. Right? That was a recurrence. Okay. Well, how did I get rid of the n? Bkn minus k. Da, 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 da. Okay, here the n is the k equals 0 term. You remember the very first term of this is n x to the n minus 1? That was it when you differentiate x to the n. Okay, now when you let k equal 0 here, remember y0 is equal to 1. Okay, so I'm going to get, you know, y0 plus blah, 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 y0 times x to the n minus 1. This is n. We just added n time. So that, phew. So we get rid of the n this way, okay? So this term is going to drop out, and now k is at least 1, right? The k is fixed, and this sum is over I. So 1 less equal k less equal n. You have to make sure you say that. Okay. So minus kck. Actually, I'm sorry. Yeah, in general, you're going to get nck. You see that? You get that as a general fact, not just at 0. The 0 thing takes care of the first term. In general, you still have the ck is cold. It doesn't have an I in it. So you're going to get the nck in both cases. Goodbye. Okay, now that's the formula you're looking for Xi. Oh, that's fine. Some number. Okay. That's the formula you want. Now, do you see anything interesting about that formula? This is a k. This is a k minus 1. That means if I iterate up to step k minus 1, I can find ck. Now I can go yk is dyk. You know what? You see the idea? So this is iterative. I know it seems like it comes out of nowhere. I think this is what Faddeev actually figured out. So notice this is iterative or whatever. I think you know what I mean. I don't know if this is a specific word. Or recursive would be better.
Were the xi's the roots? Of
The
the
xi
original,
are the roots.
so you don't know the xi's yet.
Thank you.
Okay.
You had exactly asked the right question. Now we go back and we say, wait a second. I don't know the roots, but if I have a matrix and I call the matrix A, I could take the trace of A, and that's equal to the sum of the roots without knowing the roots. That's the trick. You don't need to know the roots, you just need to know the traces. So there's a famous theorem called this. So various people can have various. There's a thing called the spectral mapping theorem. It says if I have a polynomial, say g of A, then the eigenvalues are g of. So remember, xi were the roots of the characteristic polynomial. So x1 are eigenvalues now. And then our g of xi. Now, you remember my buddy Q? So I have Q of. Remember, I have Q of xxi. And I sum this up. That's the trace of Q of x and A. Pretty cool, huh? So that's the thing that works. So you can, what you do is everywhere where you sum, you can write the matrix A. Okay? So that's the point. So for so you get minus say KCK is the trace of A YK minus 1. And that's your formula. So CK is minus 1 by K, trace of A YK minus.
So your q originally was, it was a function of x and t, and x was your variable, and
everything's
t was the
polynomial.
thing, t was the thing that you're gonna evaluate at, but it had this symmetry property.
Right.
So now this QXA, you can view A as the variable, and now this is just a
Polynomial
in
in A.
A. Yeah.
What happened to the other xi? The y of xi?
Yeah,
That's pretty good.
that's A. So xi becomes A,
That one, and the other one.
and YK minus 1 of xi is YK minus 1 of A.
Okay, so you're not writing the second A.
I didn't write this. Yeah, if you wanted to write this out,
Okay,
as a
okay.
function of A thing.
Yeah, okay.
Yeah, so the recurrence is, so YK is A, this would be the recurrence. So now you see the idea. The idea is you need, once you've got YK minus 1, you're going to need this anyway. But what you do is you solve for the CK, then you throw it back in, and you come back around. So it takes about, it's a very unique and I think, did I hand out the Python program or not? Yeah, so it's like five lines or something with Python, Even I can do it. I know nothing about Python hardly. But it's really cool. The only thing is I use normally all minuses because if you use minuses, then this thing becomes plus. So it's not really. Okay. Okay, and for the final touch. So now remember yn was the function of f of t. But f is the characteristic polynomial, huh? So what's f of A? 0. By clearly Hamilton here. Actually, maybe we almost proved the theorem in a way, right? Because you substitute any eigenvalue and you're going to get 0. Okay. Now that means 0. I think this was a comment. Remember when we got stuck and when I forgot that extra term? That's what we're going to do now. Remember it was 0. So this is 0 plus Cn. Now you have to put an I in, because they're matrices. Okay, what's AYN? This one, it's minus CNI. Now, what is CN in a characteristic polynomial? You have pi x minus xi, blah, 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 blah. X1, X2,
Okay.
and with a sign. What's the product of the eigenvalues? It's a determinant.
Okay.
So this is plus or minus det A times I. So this is the famous so-called adjugate matrix. But notice that we didn't need to know anything about linear algebra up until now. And in fact, if you want to, we declare this to be something interesting. Okay. And finally, that tells you what? Suppose Cn is not 0, then we know that our A was invertible. And this gives you for free a formula for the inverse. So A inverse is something like plus or minus 1 over Cn, y minus 1. So you'll notice in the code, you keep the previous guy. You keep the guy just before the end. Okay, so I think this is like the most elementary possible, I think, way to do it. Start with algebra 1, push it through. The key thing is this beautiful fact, right, that when you sum over the eigenvalues, you don't need to know anything what they are. Isn't it amazing?